In this video, we will talk about what improper integrals of type 1 are. And those involve situations where we have an infinite interval. So before I get into defining them more formally, I want to look back to something really briefly from the last video. So we ended our last video by stating that one of our goals is we are now going to try to evaluate integrals, either where our interval from a to b is infinite, because either a is negative infinity or b is positive infinity, or maybe both, or our function f has an infinite discontinuity somewhere on the interval because of a vertical asymptote. These two types of scenarios, what we call these are called improper integrals. So when you have an integral in which one of these two things happens, they're called improper integrals. So we're going to look at this first category when our interval is infinite in this video. All right, so I'm scrolling back. This is back where we were, back where we started. Okay, so what is a type 1 improper integral a little bit more technically, and how will we evaluate them? So this is a definition, and it begins by saying if the integral of f of x from a to t exists for every value of t that's greater than or equal to a, then we can define the integral from a to infinity of f of x dx. And the way we're going to define it is we're going to say that it's equal to the integral from a to t of f of x dx, but we're going to take the limit as t goes to infinity. All right, and when we talk about limits, sometimes limits exist and sometimes they don't exist. So this is what this integral will be equal to, this limit, provided that the limit exists. And we'll talk about what we'll write when the limit doesn't exist a little bit later. Okay, so I'm going to highlight this. So this is a key definition of how we are going to express these integrals when the upper limit is infinity. Okay, so the second part of the definition will be when the lower limit is negative infinity. So if, in this case, if the integral from t to b of our function exists for every value of t that is less than or equal to b, then we say that the integral from negative infinity to b of f of x dx is going to be equal to, and I replace the negative infinity with a t, keep the upper limit as b, and then f of x dx. And I'm going to take a limit one more time, but this time I'm going to take the limit as t goes to negative infinity. So that's what this integral is going to be, provided, again, that the limit exists. Because sometimes limits exist, sometimes they don't exist. Okay, so I'm going to highlight this one as well. So when these limits exist, we have a certain terminology to refer to them, and same thing for when they don't exist. So if the limits exist, then we call the improper integrals. Whoops. Sorry, I need to draw. I was highlighting when I wanted that the pen there. Okay, so if the limits exist, we call the improper integrals convergent. Otherwise, if the limits don't exist, we say that they are divergent. Divergent. Alrighty, so there's one more possibility of what one of these infinity or negative infinity improper integrals could look like. So the third situation is, well, what if we had a situation where it was integral from negative infinity to positive infinity? So we had both of them showing up, f of x dx. So what we do in this situation is we split up our integral into two pieces. One that goes from negative infinity to a, where a is some number, plus another integral that would then need to go from a to positive infinity, f of x dx. All right, so let's highlight this one as well. So when we split up this integral in this way, we could pick any value for a that we want. So as long as both of these integrals on the right-hand side converge, then the integral on the left, that goes from negative infinity to positive infinity, will also converge. I'll mention this again at the end of the video. Actually, maybe not at the end of this video, but at some point in one of the videos. But if either one of the integrals on the right-hand side here diverges, then the one on the left diverges as well. Okay, so let's do an example. All right, so let's look at an example. So let's evaluate the integral from 1 to infinity of 1 over x squared dx. So the first thing that's helpful to do is being able to recognize why this is improper. So this integral is improper due to the infinity. One of these limits of integration is infinite. That makes my interval an infinitely long interval. So what we do in this situation is we replace the infinity if there's an infinity, or negative infinity if there had been a negative infinity, with a t, with the variable t, and take a limit, as we saw in the definitions above. So in this case, I have a 1 at the bottom, and I'm going to replace the infinity with a t. So my function is 1 over x squared dx, and we are going to need to take the limit of this. And t is going to be going to infinity, because this upper limit of integration ultimately needs to be infinity. So now we just do this antiderivative how we normally would. So 1 over x squared, I can rewrite that as x to the negative 2. So we will get this equals the limit as t goes to infinity. And then our antiderivative is going to be x to the negative 1 over negative 1. Vertical line, and I'm going to have to plug in 1 and t into this. All right, so let's go ahead and do that. So first off, if I simplify this, this is the same thing as negative 1 over x. So we have the limit as t goes to infinity in front. When I plug in t into this, we get negative 1 over t. And then minus what we get when we plug in 1. And when we plug in 1, we get negative 1. So we're taking the limit of this whole thing. So I'm going to put a bracket around this whole thing. And now that we're taking the limit, the first thing that you usually do when you're taking a limit is just try plugging this value in and see what it gives you. So if I were to plug in infinity, I end up with a negative 1 over infinity, and then plus 1. So this is where I have to remember limits a little bit from the previous calculus class, or Math 30. So when you have something like a negative 1, a constant, divided by an infinitely large thing, that is getting really close to 0. And then you have the plus 1, so adding those we get 1. So the conceptual reason for why 1 over infinity is 0, so why 1 over infinity is 0 is I can think about the 1 being like I have $1. And then if you divide it by infinity, that's saying you're dividing that $1 amongst a really, really big number of people. So more and more people, millions and millions of people that are all splitting this $1. So how much does each person get? Well, almost nothing. That's why the limit is 0. All right, so there's one thing I want to note about this example. I just want to note, what does this mean geometrically? So this is a definite integral, so it should correspond to an area. So our function here was 1 over x squared, y equals 1 over x squared. And if we draw the graph of this function, the graph looks like there's one piece over here, and there's one piece over here. And we were evaluating the integral starting at x equals 1, continuing to infinity. So that is this, that corresponds to this area. And this region is infinitely long. It goes on forever. But based off of what we just found here is, we just found that this area equals 1, which is pretty bizarre. So I want to write that down. This example means that the infinite region on the right that we just drew has a finite area. And that's a little bit bizarre. It can take a while to wrap our heads around that. The fact that this region is somehow infinitely large, but its area is finite. So with infinity, there are weird things that can happen like this that defy our initial intuition. So there are many other examples of this in math where weird things happen with infinities. We're just going to scratch the surface here. Alrighty, so here is the next example. Let's determine whether the integral from 1 to infinity of 1 over x dx converges or diverges. And if it converges, then evaluate it. So again, we can see this is improper because one of the limits of integration is infinity. So I know I'm going to begin by replacing that infinity with a t and then keeping the other stuff the same. Whoops, sorry, instead of f of x, let's just write out my function, which is 1 over x. And then let's take the limit of this. So the limit and t is going to be going to infinity. So our integral is going to equal this. And at this point, I want to give you about 2 minutes to try this and see if you can evaluate what this ends up being. So 4, 3, 2, 1, pause the video. Pause it for 2 minutes and see if you can evaluate this. It shouldn't take too long. It should just be a couple of steps. All right, so hopefully you did that. Hopefully pause the video for about 2 minutes to try this. So we can take this antiderivative. So we get the limit as t approaches infinity. And the antiderivative of 1 over x, we will get ln of absolute value of x. Vertical line, and then 1 and t. So now we start to plug in. So we get the limit as t goes to infinity. If I plug in t, we get ln. Technically, I should write absolute value of t. It turns out I don't need to write the absolute value. I'll talk about why in a sec. But then I do minus what I get when I plug in 1. So I'll get ln of 1. And with the 1 as well, I don't need an absolute value because 1 is positive. And the absolute value of 1 would just be 1. With this first expression, we don't need absolute value since t is approaching infinity, which means that t is positive. So if I were to take ln of absolute value of t, well, the absolute value of t would just become t. So I don't need to put an absolute value around it for that reason. All right, so let's put a bracket around this whole thing. This is what we're taking the limit of. So now, like with the example before, when I'm taking the limit, first step is usually try plugging in and see what happens. So if I do that, I get ln of infinity minus ln of 1 is 0. It might be helpful to remember what the graph of ln looks like to remember, well, what's ln of infinity? So recall that the graph of something like y equals ln of x looks like this. It has a vertical asymptote as you approach, as x gets really, really close to 0, and this x-intercept is at 1. So the part that we care about is, well, what's happening as the input gets really, really big? So as the input gets really, really big, as x goes to infinity, ln of x is also going to infinity. The y values are also going to infinity. So ln of infinity is infinity. So we get infinity minus 0, which is infinity. So because our limit ended up being infinite, that means our integral diverges. So we've now seen an example of an improper integral that diverges. Alrighty, so I want to talk about, well, what does this mean in terms of areas? Because we did it with the last example with 1 over x squared. What does it mean with 1 over x? So I'm going to quickly draw these pictures again. 1 over x squared we had seen. There was one part of the graph here, one part of the graph there, and we were finding the area from 1 onwards to infinity, and that was this region's area. And what we saw was this area from the previous example was 1. What the graph of 1 over x, so if I draw some axes and I draw 1 over x, this one's a little bit more spaced out. A little bit more spaced out. There's one other piece here. This is a hyperbola graph. And I look at this. Again, it's going from 1 to infinity. So if I shade in that region, again, it's going from 1 to infinity. This one's larger because this orange region is sort of, extends higher up, because the graph of 1 over x extends higher up. And moreover, it's weird, but it turns out this one is actually infinite. This one is actually an infinite area. We just figured it out up here. This limit ended up being infinity. So for perspective, I think it's helpful to graph these on the same set of axes. So I'm going to do this in Desmos. So I'm going to color in y equals 1 over x first. And notice that there is that graph. So we'd be talking about the area starting at the line x equals 1, and then everything to the right of that underneath this graph and above the x-axis. And it turns out if you keep going like this, it ends up being infinitely large. But if I draw in y equals 1 over x squared and compare it, here's 1 over x squared. Look how much lower it is than the blue graph. It is significantly lower than the blue graph. So seeing these graphs like this, it can be a bit more reasonable to see, well, why is the area under the green graph so much smaller than the area under the blue graph? And we can see this conceptually now, because with the graph of 1 over x squared, if I just delete it and shade it in again, 1 over x squared, as x gets really, really big, that graph approaches 0 so much more quickly than the graph of 1 over x does. As x gets really, really big, the y values still get close to 0, but they take a whole lot more time to do that, which builds up all of this extra area that the green graph doesn't have. All right, so back to our notes. I just want to write that down basically. So conceptually, as x approaches infinity, 1 over x squared approaches 0 much more quickly than 1 over x does. And as a result, so that arrow just means this means the area under 1 over x squared is significantly smaller. We could only really see that it's finite here after evaluating that improper integral, but hopefully by looking at the graphs, it might make a little bit more sense. Like, why is that even possible? Why is it possible for one of these to be infinite and the other one to be finite? Alrighty, so in the next video, we will do another example, but that's more challenging.